Video on the channel. In today's video we're going to be showing you how to solve the logistic differential equation. Now as you can see up here, I clearly cannot spell, so let's just ignore that. What we're going to do is focus on this type of equation. Now it's a type of differential equation that appears in separation of variables, and it has the structure like this. This is the example we're going to be solving today, but it generally looks like this. Now a logistic differential equation is basically when you're dealing with population versus time. So let's say we have a population time graph. When the population is at a certain, let's say, amount, it's going to increase to that value up there, and it's going to stabilize at it. Likewise, it could also have an amount like this and go down to an amount like that. So basically, it's going to have a general shape like this, a function of p. So this would be p of t. And pretty much when we solve our differential equation here, we're going to get that function as pretty much of time. Population is a function of time. Now, a couple things if you want to know about the background about this differential equation. So P represents population at time t. R is the, I don't even know how to pronounce that word. It's basically the growth rate of the population, so like a factor. K is the carrying capacity, which is pretty much the maximum population of the environment can sustain. And T is time, okay? So as a general thing like this. Now here we can spot that in this example here. So in this case here, the growth rate is 0.2. The carrying capacity is 500, okay? So let's just solve this differential equation, okay, as an example, okay? So let's go down here. Now what we want to do is we want to separate our variables, okay? Now we can see here we have our independent variable t, but we don't have any t's here. So what we have to do is move everything to this side and move the dt, the differential, to that side, okay? So by doing this, we're going to get dp over 0.2p times by 1 minus p over 500 equals dt. Now, the best thing to do at the moment is to convert the decimals into fractions or fractions into decimals. Now 0.2, same as 1 over 5, so we're just going to switch it to that, okay? Now, because we have, oh, not p, 5. Now, because we've separated everything, we can actually integrate both sides, and we don't need to attach a differential because we have a differential on both sides already. So all we have to do is just attach the symbol here, and we can start solving. Now, this side's fine. This will just turn into t. Now, this here is quite a tricky integral on its own. 1 over a fifth p, 1 minus p over 500 dp. In order to integrate this, we actually need to do partial fractions on this actual function here, okay? So this is what we have to do, okay? So what we have to do is pretty much go 1 over 5p, 1 minus p over 500. So we can see here we have two linear factors, which is this guy here and this guy here. So we can break it into two fractions where the denominators are going to be these linear factors. So 1 over 1 over, oh, well, not 1, we don't know what that is on the top there. A over a fifth p plus b over 1 minus p over 500, where a and b could represent any number pretty much, okay? So what we have to do first in order to find these guys here is we're going to substitute specific values of p to eliminate the other variable, okay? But before we can do that, we want to multiply both sides by this entire denominator here, because if we start plugging in values of p, we're going to have divided by zeros everywhere, okay? So that's why we want to do this. So times both sides of the equation by this whole thing here. So what we'll be left with is 1 on this side here. Here, that 1 on 5p will cancel on the top here. So what we'll be left with is a times by just the other linear expression here, okay? And likewise with this guy here, b, and you'll have a fifth of p. Because when you multiply both sides by this, the opposites are going to cancel here, and likewise here, okay? We've just kind of skipped that step, okay? But it is pretty much present there, okay? If you want it in a bit of detail, I'll just write it here. So what we effectively just did was we went this times by pretty much, well, I'll just make it smaller so we can fit it all in. And then I'll just effectively copy just this side here. So when we multiply that, that would cancel with that, and all we would be left with is just that there. And then same thing here, that would cancel with that, and all we have is pretty much that there. Okay. Alright, now we're here. Now in order to find A and B, we can substitute values of P. So here, if I want to find what B is, I want to get rid of the A. In order to do that, I want to make P equal to 500. Now, the reason why I want to make it equal to 500 is because if I go 500 in there, I'll have 500 over 500, which is 1. 1 minus 1, that whole thing will turn to 0 when P equals 500. So let's just do that. So you have 1 equals A times by 0, effectively, plus B times by a fifth of 500. Okay? Now, 500 divided by a fifth is 100. Okay? And hopefully you should, oh well, not divided by a fifth, times by a fifth is effectively dividing by 5. So what we have is 1 equals 100B. Therefore, B is 1 over 100. Okay? Now let's do the same thing with A. In order to find A, I want this term to be 0. Now this is quite easy. I can just let P equal to 0, because that'll just be 0 there. Okay. Then in this case here, we'll get 1 equals A times by 1 minus 0 over 500 plus 0. So here we get A is actually equal to 1, because that disappears, so we have A times 1 equals 1, so A is 1 in this case here. So now we know what the partial fractions are. So here, if we just go here, copy that, bring that down, we can fill in the blanks pretty much, okay? So this can go there, and this can go there. Now we can clean this up algebraically before we integrate this. So we have 1 over a fifth of P plus 1 over 100, 1 minus P over 500. So what we can do here is 1 over 1/5 is the same as 5, okay? So here we can rewrite just this term as just 5 over P, and here we can effectively just move the 100 down here, okay? So what we'll have is plus 1 over 100, 1 minus P over 500, okay? Now, I think we can leave it like this for now. If we want to, we can multiply that out to make that a bit better, so we can multiply that out through there. So we'll get 5 over P plus 1 over 100 minus, and here you're just going to have P over 5, okay? Because 100 divided by 500 is still going to give you a fifth, okay? Alright, so let's simplify that. So that, coming back up here to our differential equation, we're still trying to solve, okay? So all that was just algebra, okay? So we'll go back here. Let's go here. And then all we need to do is just substitute this into there. So we have the integral 5 over P plus 1 over 100 minus P over 5 dP. The integral here is just going to be T. And we'll just leave a constant here for now, okay? Constant 1, okay? Now here, integrating this, we can integrate them separately. So this will turn into 5 natural log of P. Here, we need to divide by the differential of this guy here. Now the differential of that would be negative 1/5. Now if we're dividing by that, we're going to have pretty much, instead of negative fifth, negative 5. So here we'll have negative 5 ln 100 minus P over 5 plus C2 equals T plus C1. Okay? So hopefully you can see what I've just done there. So those turn into that. Okay? Now, what we can do if we want to is we take our factor of 5. So we have ln of P minus ln of 100 minus P over 5 plus, now here I'm just going to move the C to that side here. So instead of writing two C's, I'm just going to combine them as just C in general. So here I'll be equal to T plus C, where this C here is effectively C1 minus C2. Okay? Right. Let's combine this using the log law. So if you're minusing two logs with the same base, you can divide the inside. So this will be divided by that on the inside of a natural log. So 5 ln. Now you're going to have the absolute values here because you can only have positive inputs in here. Minus P over 5 equals T plus C. Now we effectively want to make P the subject, which is in its own little problem because we have P in multiple places, but all it requires is a little bit of algebra. So what we're going to do is multiply both sides. by pretty much 5 to get that 5 over there. So we have ln p 100 minus p over 5 equals 5t, and I'm just going to write c now. So this c is now different to that c, it's 5 times bigger. Okay. What we can do is raise both sides to the power of e, and that effectively cancels that. So we're left with this p over 100 minus p over 5 equals e5t plus c. Now what we can do here is e to the 5t plus c is the same as ec times by e to the 5t, and we can just write that as another constant. So we'll say e to the c is a, so we can just rewrite effectively that right hand side as just, I'll just copy this first, a e 5t. Oh wait, let me just check I did the algebra. Sorry, that's meant to be a fifth, not 5, because I divided by 5. That was nearly a bit of a mistake, so that's a fifth. Doesn't change it anyway. It literally just, well, it will change in the long run, but the algebra we just did there doesn't really change. Now, what we want to do is get p by itself. So what we want to do is multiply both sides by this to effectively move it up there, and we're going to expand that. So we'll get p equals a e, I'm going to write that as 0.2 t times by 100 minus p over 5. So we can multiply that out. So we'll have p equals 100 a e 0.2 t minus, we'll just go p over 5 a e 0.2 t. Now that we've multiplied everything out, we want to group up p. So here p is here and p is here. So we want to move this side, this thing to the other side, and we'll factorize that p out. Okay, so we have p. To move this to the other side, we have to plus it. So plus p over 5 a e 0.2 t equals 100 a e 0.2 t. What we can do here is we can factorize a p, so we get p 1 plus a over 5, I wrote a twice, e to the 0.2 t equals 100 a e 0.2 t. We can now divide both sides by this, so we get p equals 100 a e 0.2 t over, and then literally just all of this. I'm just going to be lazy and copy it, and I'll just put that there, and there you have it. If we wanted to make it a little bit better, just trying to think, we could times the top and bottom by 5 if we wanted to get rid of that fifth there, and this is effectively timesing it by 1 because I'm timesing top and bottom by 5. So if I did that, that'll get rid of that fifth, and that'll just turn that to 5, and that'll turn that to 500. Okay, so we'll get p equals 500 a e 0.2 t over 5 plus a e 0.2 t, and that is our general solution to the logistic differential equation built like this. Okay, so pretty much all we need to understand about this guy here is that the growth rate is present in the general solution, like the 0.2 is present in the answer, and so is what, the carrying capacity? Yeah, the K. Okay. But yeah, that's how you solve the logistic differential equation as an example. Okay. If you have any questions about this one here, leave something in the comments and I'll try my best to answer it, but I'll see you in the next video.